Hello ladies and gentlemen, welcome to this video in which I will be sharing the evidence which proves that the number of days in a year is not 365 and a quarter that we have been told that it is ever since we were kids. In presenting that evidence, I will rely on only two items of data. The first item of data that I'll rely on is the fact that the period from the rising of the sun to its next rising averages 24 hours. This is a fairly well-known fact. The period from the rising of the sun to its next rising is technically referred to as a solar day. The second item of data that I'll rely on is less well known, and it is the fact that the sky rises and sets in the same way that the sun rises and sets. In order to track the rising and setting of the sky, we normally select a star that is affixed to the sky and then track the rising and setting of that star. The period from the rising of such a star to its next rising is referred to as a sidereal day, as distinct from a solar day. And it lasts 23 hours, 56 minutes, and about 4.09 seconds. So the first step in this proof is a small exercise I'd like you to do, if you don't mind. Search the internet for the number of hours in a sidereal day to the highest precision that you can find. Then divide what you get by the difference between the hours in a solar day, namely 24, and the hours in a sidereal day which you just found. I bet you that the result you get will be very close to 365 and a quarter. Basically, it will be the number of days we have been told are there in a year. That number of days is normally referred to as a solar year, and we shall going forward refer to that period as a solar year. So the question is, how is it that such a simple division is able to give us the number of days in a solar year? What does that division actually represent? To understand what such a division represents, imagine two athletes running laps around a circuit. The first athlete completes their lap in 45 minutes, while the second athlete completes a lap in 1 hour. We'd like to find out what is the number of laps which the slower athlete will have completed by the time that the quicker athlete first catches up with them after they begin their laps from the same place at the same time. This is a fairly straightforward exercise and we'll just do it mentally. After 1 hour, the slower athlete will have completed their first lap. The quicker athlete will have completed their first lap and gone some ways into their second lap. In actual fact, they will have gone 1/3 ways into their second lap, because if in 45 minutes they are able to complete a lap, then it means that in 15 minutes they will complete 1/3 of the lap. So at the end of the second hour, the slower athlete has completed their second lap, while the quicker athlete has completed their second lap and gone 2/3 ways into their third lap. In the next 1 hour, the quicker athlete will complete their third lap in the first 15 minutes, and in the remaining 45 minutes will begin and also complete their fourth lap. In the third hour, the slower athlete will complete their third lap. So it means that at the end of 3 hours, the quicker athlete and the slower athlete will both be at the beginning of a lap, and the quicker athlete will have caught up with the slower athlete. Therefore, we can say that the slower athlete will complete 3 laps by the time that the quick athlete first catches up with them. And this is the information we were looking for. That result can also be obtained simply by dividing the number of hours that the quicker athlete takes to complete a lap by the difference between the number of hours that the slow athlete takes to complete a lap and the hours that the quick athlete takes to complete a lap, namely 45 minutes divided by 15 minutes. The result is also 3. So applying this analogy to the situation of the sun and the star, and if the star is equivalent to the quick athlete and the sun is equivalent to the slower athlete, then we can conclude that dividing the hours in a sidereal day by the difference between the hours in a solar and the hours in a sidereal day gives us the number of laps or circuits or days which the sun will have completed by the time that the star first catches up with it. And this, ladies and gentlemen, is what we have all along been told is the number of days in a year. Going forward, we'll refer to that period as a solar year because that's what it's technically referred to as. So what we can say is that a solar year is the interval of time that it takes the star to first catch up with the sun after they begin their circuits at the same time when measured in days. So this has two things that are noteworthy about it. The first of it is that if the sun and the star begin their circuits at the start of the day, then the time when the star first catches up with the sun will not be at the beginning of the day. That's because there's a fraction in the number of days in a solar year. Which raises the question, is it possible that after several instances of catching up, of the star catching up with the sun, is it possible that a time will come when the star will catch up with the sun at the beginning of the day again? That is important because if such an instant exists, then it would mean that we have identified a cycle. Because if it exists, then it means that the star will be with the sun at the start of the day. And that is the point when we began our count. So basically we will have identified what we might refer to as a cycle, if it exists. And there really is no reason to expect that it exists, but we can check if it exists. So the way to check if such a thing exists is to say that the first instance of catching up will be after the duration of a solar year, which is 365 point whatever it is you got. If there's a fraction, then we go to the next. After 2 cycles, after 2 solar years, when will it catch up with it? After 3 solar years, we do the same. And we may continue that multiplication until we run into an instance where that multiplication gives us a whole number. Because if it gives us a whole number, it means the star has caught up with the sun at the start of the day again. So I have done that math myself, and I can just inform you that what you will get is that when you multiply a solar year by 293, you get a whole number. The number that you get is 107,016. So there is a cycle in nature, existing in nature, that lasts 107,016 days. And in that time, the sun and star return to the same place relative to an observer who is on the earth. This is very important. So previously we were told, we identified that we have been told that the interval of time that it takes the star to first catch up with the sun is what constitutes a year. And it lasts 365 and some fraction of a day. But what if what if there is a different period of time, which is a whole number of days, and which fits exactly into that cycle? How many days would such a year have? And the reason why that question is important is because if you look at the way that human beings measure things, they always select first a basic unit of that thing and then give names to convenient whole number multiples of that thing. For example, when measuring distance, the basic unit is a meter, and then a higher unit is a kilometer, which is 1,000 meters. It's always a whole number multiple of the basic unit. This is what works for humans. In my community, we measure grain, for example, in tins. This tin is called a gorogoro. So 8 gorogoros make a debe, and 5 debes make a sack. It's always a whole number multiple of the basic unit. But in the case of time, the basic unit, we do not define it. It's given to us by nature. It's the day. So ideally, if this was to work conveniently for us, we would be looking for a year that has a whole number of days. And we would be looking for such a thing in nature, because we don't control that cycle. It's just given to us by nature. So we will be looking for such a thing. And what I'm really saying here is that, might there exist such a thing? Can we look for it? So my proposition when doing this activity was this. I suppose that 365.25 is not a year, but it's 1 year plus a fraction of 1 year. And that fraction of 1 year in 293 instances cumulates to a whole year. So I'm looking for a year which has less than 365.25 days, but where the difference between that year and 365 and a quarter is a fraction of that year. And that fraction cumulates in 293 instances into a whole number. So that we would have, a total of 294 such years in 293 solar years. And the question is, how many days would such a year have? And when you divide it, you'll find that 107,016 divided by 294 will give you exactly 364. And 364 is extremely convenient because 364 is exactly a week of 7 days times 52. So that in the natural way that human beings measure things, we would say that the basic unit of time would be the day, and then 7 days would make up a week, and then 52 weeks would make a year. And the other convenient thing is that this 364, this year of 364 days, 294 of them make up a cycle. And 294 is actually 49 times 6. And 49 is 7 by 7. So basically we are saying that the system of measuring time would be, the basic unit is a day, and then 7 days make a week, and then 52 weeks make a year, and then 7 years make a week of years, and then 7 weeks of years make a jubilee, which is 49 years, and then 6 jubilees make a cycle. And that would be perfectly convenient for human. It's so perfect, in fact, that one cannot help but wonder, could this have actually been created so that it serves us human beings? And that, ladies and gentlemen, is the evidence which I have been presenting. The last item I'd like to highlight is that a year that has 364 days would result in every date falling on the same day of the week forever. So if, for example, the first of the third month would be Tuesday, then in all years it will always be a Tuesday. And that's again super convenient. So I cannot help but wonder, does the existence of such a measurement system result purely from chance, or could this have actually been created intentionally so that it would serve human beings? I find it very difficult to imagine that such a perfect system for the needs of human beings just came about by random. And that really is the issue that I have with this whole system. Thank you for watching and have a nice day.